Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future watching us on the recordings. My name is Gislain Fourny. I'm going to be here with you during the semester to dive into the beautiful world of big data, or at least I hope you will find it beautiful once the semester is completed. Today is a bit special because, and tomorrow as well, because in the first week I just don't dive directly into the actual big data material. What I like to do is start with an appetizer, like a historical perspective on big data. How did we arrive here? And a brush up on relational databases and SQL, which I assume a lot of you already know a little bit. So in big data, we speak a lot about scale, right? And in fact, at the end of the course, you'll be able to query gigantic amounts of data. You'll know how to query gigantic amount of data, but not just gigantic, also messy, in the sense that it might not be in normal form or highly normalized as what you learned in the relational database course. It might be a bit messy, and it's part of the deal that it's messy. You need to clean it up, normalize it, structure it, maybe to feed it into some machine learning model. So you'll be able to query gigantic amounts of messy data, but not just that, you will also understand how it actually works, the whole infrastructure that is underlying these technologies. You might have heard of some buzzwords. You might have heard of Hadoop. Who heard of Hadoop? Okay, Spark? A lot of you as well. RumbleDB, JSONic, maybe a bit less because it's homemade right here at ETH. 20 plus students, some of you, worked on it and built this, and now we're actively using it in the lecture. It's kind of a wrapper for everything else. And JSONic is a language that allows you to query it. Actually, this was JSONic. All right, but big data is a lot about scale. So when you think about scale, you might think also about the universe. I think that's the particle collision at CERN. But if we start at our own scale, roughly a human being is somewhere around 170, 180, 190 meters, right? Now, if you go all the way to the Earth, you might know that the circumference of the Earth is 40,000 kilometers, roughly. In fact, it's almost a round number. So you might be wondering why. It's actually not a coincidence. It was defined in that way, in such a way that a kilometer is such that 40,000 kilometers is a circumference. All right. And then if we convert it to some other units, because kilometers everybody knows, metameters, maybe a bit less, right? Megameters. You might know mega from megabytes, right? But we can also use it, in fact, on any other unit. So the Earth is already in the megameters range. And if we continue to zoom out all the way into the solar system, the distance to the sun is about 150 gigameters, 150 million kilometers. So these are gigameters all the way to the Earth. If you go to Jupiter, you are already in the terameter range. The entire solar system, actually, I'm very generous because it's actually a bit beyond the solar system. We reached the petameter. And with, I think it's 10 petameters, we are at 1 light year already, right? But that's already the peta prefix. If we continue to zoom out beyond the solar system, the entire galaxy, the Milky Way, that's not actually it. We are unable to take a picture like that, but it's inferred from what we see in the sky. So we are at 1,000 hexameters, which we can actually already compress to 1 zetameter. We have prefixes for everything, you see. And then if we expand all the way to what we can see, because we are not even sure that's the end of it, maybe even bigger than that, but what we can see, because the light actually reached us, that's roughly 13.8 billion years, the age of the universe. So we are looking at 138 yottameters, right? In fact, if you even consider the expansion of the universe, it might even be maybe 200, 300, 400 yottameters. All right. Okay, press the button. So when we looked at these scales, the entire universe, it also forces us to think at very small scales. In fact, this is exactly what we are doing when we try to reproduce these conditions. We are looking at particle physics, right? These super tiny particles that form matter, right? And so this is the standard model in physics. It's the best that we have, recently completed with the Higgs boson. In fact, I'll come back to it, but finding the Higgs boson is a database problem, right? We collect the data, and then it's a database problem to actually exploit the data. But we have to look in the infinitely small as well to understand the infinitely big. And this is why I like to have this analogy between physics and data science, or to almost look at it like a chemistry problem, right? We look at data, we manipulate data just like atoms and molecules. And we will see you can actually consider that there's also atoms and molecules of data. So physics studies the real world, and data science studies the data world. In fact, I like to think about it as a matrix, which I will show you soon, but I think I planned a question here. That's why I have this slide. So this here is an application of ETH called the Edu app that I can ask you to ask interactive questions. You can participate from here in the room on your smartphones, on your computers. You can also do it from Zoom if you're watching us over Zoom. And all you need to do is either go to one of these stores to find Edu app 3, or you can go in your browser to eduapp-app1.ethz.ch. The first time I'm going to give you a bit of time, but then you can just save it in your bookmarks or favorites to have it ready. Okay, so I just leave this, giving you the time to go there. Then I'll move over to this first question, should be an easy one. So what is your main background? Are you a computer scientist? Are you a data scientist, computational biologist, or maybe a different background? I'll give you some time to figure out how this works. And hopefully, we'll start seeing answers coming in. If I start it, of course, because if I forget to start it, that cannot work. It actually agrees to start. Oh, do we have a demo effect here? That's the live effect. Ah, the network. No, that worked. Wonderful. Okay, so we have a lot of computer scientists. Data science, I mean the master students in data science, right? So master students in computer science, master students in data science, masters in computational biology. So I'm giving you a bit of time to figure it out. Then the other times it will be straightforward. Right, 42. So in total, there are 370 of you registered for the course, maybe even more by now. 47. 62. That already gives a good idea, right? So the majority of you are computer scientists, and some of you are data scientists. It's a program we introduced in 2017, data science, and computational biologists with computer science skills. All right, let me stop here. You'll have more opportunities to use the app already today, and it will be much quicker the other times. So let me switch back to the slides. And normally, if I prepared everything correctly, if I did my homework, we should go exactly to where we left, except if there is a demo effect, which is here to give you the perspective on things. So We had to split big data into big data and big data for engineers because in the first year, it was very popular, not just in computer science, but in other departments. So this course is for computer science and data science master students, as well as computational biologists. There are a few exceptions, for example, for mobility students. If you're not a computer scientist or data scientist or could not register, it probably means that you should take big data for engineers in spring. But if you really want to take a course this fall, you can also take information systems for engineers. Information systems for engineers is basically the relational database lecture, the same that computer science gets in the bachelor's, most of you, but targeting the other departments, right? So this is the overview of all of the courses. Now, here's the matrix I wanted to tell you about how we do science. A long time ago, we didn't have machines. And so we knew mathematics and physics mostly, right? That slowly emerged. Mathematics is a lot about theory and thinking and manipulating numbers, proofs, and so on. Physics is more about experimenting. And if you think at it from a philosophical perspective, and of course here there might be different opinions, mathematics could be, in terms of modal logic, considered as necessary, meaning all you need to do is sit on an armchair and think, and you can just derive everything. Physics, normally you can't. Of course, there's theoretical physicists doing it on a whiteboard and on an armchair. It actually works well as well, but at some point you need to experiment. The reason you need to experiment is that in physics, you're looking at the world as it is that you need to figure out, as opposed to how it could have been. But it could have been, but it's not, right? So you need to run experiments for that. And in a way, what we have today, computer science, which is a lot about like computational ability and all these problems, is the theoretical part when we need a machine, where we use a machine to do our things. And data science, I like to think of it as the physics of computer science. Data science is just like physics. It's about running experiments, but experiments by querying the actual data in order to understand the world better. Because without the data, you just cannot figure it out from your armchair, right? You need to look at the actual data to understand the world, right? So these are these scary words, necessary, contingent. It's all about modal logic. All right, but this is my high-level view. We had a lot of wisdom already a long time ago from Plato, who told us that a good decision cannot just be based on numbers. You also need knowledge, right? So it's all about what information you extract and what knowledge and what wisdom you extract from the data. So let me start with a historical perspective on databases. Let's start with the prehistory, and then I will tell you what the year zero is, the year one. There's no year zero. The year one of databases is going to be. So if you go to as far back as you can about when we first stored data, you probably will think of our brains, right? When we could speak, we could sing. Actually, people sung a lot about these things in order to tell about epic battles and everything that was happening. A lot, of course, about the kings and the pharaohs and so on. And so the knowledge was propagated by speaking. And every generation would just transmit and transmit and transmit the knowledge. In fact, you could even go further than that. If you go beyond human beings, the DNA is also some kind of data, right? Not in base 2, in base 4, but you could also already consider it as some kind of data or database. All right, but there is a problem with this, because if you just speak and sing, information can get lost, can be distorted, and so on and so on. So this has problems. And in fact, this is the reason why we don't know much about what happened before we invented writing. Writing was a revolution because this is when we actually start having information that did not get lost or distorted, right? And the most ancient writings that we could find are typically on clay tablets that look like this one. It was basically humans found a way, our ancestors found a way to store knowledge in a way that would be preserved over long periods. If you look at these tablets, there's actually two kinds of information that you can store on these tablets, or two shapes of data. We'll come back to the shapes of data. The first one is text, just like here, right? You tell a story, these are words, and it's very linear, right? But there is a second kind of tablets I find extraordinarily exciting, which are looking like this. This is Plimpton 322. It almost looked like tablets that we have. Well, technically, it is a clay tablet, but it looks like a tab or I don't want to say a brand, but you probably know what I mean. It almost looked like a spreadsheet software installed on a tablet. In that case, it was Pythagoras triples, the size of a rectangular triangle that was very useful in order to triangulate real estate. For example, whenever there was a flooding, you need to keep track of who owns what land. And so this is the sort of knowledge we stored. But this is incredible because this is a relational database. This is a relational database, and it is thousands of years old, right? This is how tables actually are very, very old. They didn't wait for computers to actually exist, right? And a database doesn't need a computer. The database is the data itself, right? So this is a relational database. There was still a problem with clay tablets or papyrus and all the technologies we had, is that if you want to make copies, then you need to make them one by one. There was even people working full-time, especially monks, copying and copying and copying these things. And the invention of the printing press changed everything because suddenly you could make massive amounts of copies. And this is how the golden age of the written press arose with all the newspapers a bit later in the 19th century, right? So printing was also an accelerator to copy data without errors. Then we had computers, but in fact, computers almost look boring because all they did was just automate and accelerate things, especially with the invention of the silicon and semiconductors. So we just started to automate a bit the processing of the data. So this gives some perspective to think that the computers back then were absolutely gigantic, the 50s, 60s. They would consume the electricity of the entire city. They would even black out when you switch it on. But the worst part is that the electricity that it consumed is by way less than just a smartphone today, probably even less than a smartwatch. So this is just incredible. Or maybe not the energy, but the computer power has consumed a lot of energy. All right, so these are the computers, which brings us to the 1960s, where we started processing data with screens, but the way it was done was that we would store the files in directories, organized as files, and we would just directly process them with some programming language. That was actually quite cumbersome. I'll come back to this because some people today are doing exactly this, using Python in order to query local files. And one of the things that I would like you to realize is that, in fact, when we are doing that, we're getting back to the 1960s because there are much better ways than to just use a programming language to query files directly. And then was history. Year one of databases is 1970 with a person called Edgar Code who had a brilliant idea. Edgar Code realized that you shouldn't expose the complexity of the files and programming languages and so on to the end user. The only thing the end user should have to worry about is the table model. Anybody can understand a table. It's thousands of years old. Thousands of years ago, they could already understand these things. So this is a very natural thing to do. And so if you interact with a database system to process data, you should do so at the abstraction of a table, right? A bit later, it evolved a little bit because tables reached their limits. And in fact, that's why big data came, because there are other kinds of technologies than relational databases. There are also key value stores. We'll look at them next week. We'll look at column stores, white column stores as part of the lecture in a few weeks, document stores, MongoDB, you might have heard, triple stores, graph databases, and so on. So now there's a lot of technologies, but I will still come back to that principle of isolating the user from the physical details, right? And this principle is actually called data independence. And I will probably use the expression data independence all the way during the entire semester. Data independence, right? This is super important. And data independence means the user doesn't know about all the details of how this is stored. All the user sees is some data model instantiation, like a table. All right. Now, big data. Big data is a buzzword. At least it was a buzzword, maybe a bit less today because some other buzzwords like AI and ML and blockchain probably took over. But big data at some point was a big buzzword, and that makes it actually quite difficult to define what it actually means. It also involves a lot of different companies. It's not that I'm running advertisement, I'm not paid for that. It's just that the reason why these things happen was because companies started having problems with the quantity of data that they were dealing with. So this is the reason why some of these technologies were actually invented by companies. But a lot of that is open sourced. So we'll also use a lot of the open source technologies that are available, right? Okay, now big data. Something you will see almost in any lecture about big data is the 3 V's. The 3 V's means volume, variety, and velocity. And I'm going to go through them. The 3 V's show the evolution of database systems across, I would say, the last 20 years. Maybe it started maybe in the early 2000s, all the way to today. So volume, variety, and velocity. There is a fourth one called veracity, which is a bit orthogonal, which is about the correctness of the data. But I'm going to focus on these 3. So first, the volume, the first V. The volume basically happens to us. I don't know how I can put it better than that. It just happens to us. We just accumulate data because we create it, and it's there, it keeps accumulating. And it accumulates because we can. We have the technology, we have the software, we have the hardware, we have the infrastructure, right? Whether we should is another aspect, right? Data protection and laws and privacy, this is also very important. Here we focus on the technology. There is a course called Big Data, Law and Privacy that explores this aspect. But basically we can do it. And the reason is that data has value, right? This is the reason why many things are free, right? Because they get your data in exchange for it. So data has a lot of value to be exploited. And in fact, it also has scientific value, right? Even to do science, like the data that we get from CERN in order to find the Higgs boson also has an enormous value. Also, data tends to have a utility that grows more than linearly, in the sense that if you put data together with data, what you can do with it exceeds just the sum. And the reason is that you can do a join. You know what a join is, right? That's something that comes from the relational database, relational algebra. So if you put data together, it has a lot of power. This again should be put in the perspective of data protection and privacy, because that also has an implication for that. Another aspect is what we call data totality, because today when you build a new website or a company that compares flights or compare hotels and so on, then you need all of the data for it to be interesting. And in fact, today we can do that because again, we have the infrastructure. Here's your first homework for the semester. And you've been sitting, you've been listening, but this is the first thing that I would like you to do. Make sure you learn this by heart. These are the prefixes. Now you probably know a lot of them, right? Kilo, mega, giga, tera, penta, peta, hexa, zeta, maybe these less, right? But the first, all the way to peta, I'm sure you know. Who knows them already? Okay, so hexa, zeta, iota, maybe you didn't know them. Rona, queta, they actually were invented less than a year ago. This is very recent. This is because physicists already managed to break the iota, so they needed something with 27 and 30 zeros. I think it's for the mass of Jupiter, something like this. But we'll be very happy as data scientists to also talk about Rona bytes and queta bytes whenever that starts making sense, right? So you must know this by heart. Here's a little trick. Who knows Greek, a little bit Greek numbers? Happens in geometry, right? Here's the trick. How do you say 4 in Greek? Tetra, right? Look at tera. There's 4 groups of 3 zeros. 4. So tetra, tera. Peta is like penta, 5. Hexa is like hexa, 6 groups of 3 zeros. Hepta, zeta, this one is maybe a bit less close, but basically everything is done. Even the rona is like nona. You see, it's all done in such a way that it resembles a little bit the number of group of zeros groups of zeros in Greek. So that's a little trick to just remember them. All right. Now, let's take the clicker app again. Let's try to make it much shorter than last time. If you are already ready to click, I'm going to get back to the browser right here and start this one. So what do you think is big data? And I hope the network is my friend here, if that actually works. It's the first semester day, so if everybody is using the Edu app at the same time, in other lectures as well, there might be some delays. It should update at some point. At least we didn't get any complaints from Zoom, so I assume that the network is fine. It's really just the Edu app that is hanging a little bit. Let's give it a few more seconds, otherwise I'll just move on. All right, no, it won't do it. Okay, let me ask you then, what do you think? Who thinks a gigabyte is big data? Okay, who thinks a terabyte is big data? Okay, who thinks a petabyte is big data? Ah, we have a majority here, an exabyte? Okay. The consensus, as you saw, seems to be on petabyte, and this is actually general, not just in this room. The petabyte is what's considered big data. In fact, there is a reason, is that this is what you cannot store in the same machine, right? Terabyte fits on a single computer. Petabyte, you need a data center, and we'll talk about data centers. Exabyte now, some companies are actually starting to reach that, but this is a lot of data, right? So exabyte, zettabyte, you're talking at humankind, almost at that scale. All right, so let me, oh, it's actually started working, which is great because now we have more of you who managed to answer. All right, let me come back to the slides. And again, if I did my homework correctly, we should get exactly where we were. There you go. So petabyte is roughly where we think of big data, where we are. However, I'm going to already say it today, even if you have terabytes or gigabytes, it might still make sense to use big data technologies. One of the things that I would like you to understand is that you can also use big data technologies right here on your laptop. You don't need a data center, and we'll show it with the Spark and RumbleDB, works very nicely on your laptop as well. And it already helps to be faster. Why? Because your computers have several cores, right? And so with big data technologies, you can spread it over the cores of your machine, right? All right, but what's incredible is that what took us thousands of years to achieve in physics, all the way with Hubble to the cosmological scales, took us just a few decades in computer science in terms of using the prefixes. And that in itself is amazing, the acceleration, right? Okay, this is just for those of us who are geeks, that includes me. We love to have powers of 2, and at some point, people were saying kilobytes, that kilobyte is 1,024 bytes. But somehow these prefixes normally, or they are no longer here, the prefixes should be powers of 10. So at some points, it was cleaned up, and people came up with different prefixes for the powers of 2, right? So it's in increments of 10 to the power of 10, 20, 30, and so on. It has the same number of digits. At the beginning, it's close to the powers of 10, but you see there is a 26% difference when you arrive at the Quebi bytes, right? These last two is not finalized. There was a proposal to call them Robi and Quebi, but it's not approved yet. All right, that was volume, right? So you need to know the prefixes. Next come variety. I already told you about the table. Everybody understands the table. In fact, if you run polls with people understand tables more than they understand pie charts, right? This is really something universal. But as it turns out, tables are not the only data model out there. It's not the only data shape. In fact, there are also trees. And we look at trees a lot in this lecture because trees can be seen, or collections of trees can be seen as data that is not in normal form. And that is part of what I would like to show you in this semester. So trees, you can also think XML, JSON, YAML, and so on, right? Then we have graphs, and we also cover at the end of the semester graph databases like Neo4j. We have cubes, so we also cover data warehousing and how we slice and dice the data. And the fifth shape of data is text. Text, technically, I also consider it a database problem, but this is information retrieval. Who here took the information retrieval course? All right, so you already know how to query text, right? We spent a semester on that, but that we won't do in big data. This is just to mention. So 5 shapes of data: trees, tables, cubes, graphs, and text, right? Unstructured data. This is very important. It might be that there are other shapes that will start appearing, but most often it's not really new shapes, it's just variations of the existing shapes, right? So these are the 5 elementary shapes of data. And based on these shapes, we will be able to define data models. So this is the variety. And these shapes became extremely popular in the past 20 years, I would say. Next, velocity. That's the speed at which we produce the data. And in order to give you an impression of what actually happened, it's also something that happened to us. I will use 3 concepts with specific names. People may call them differently, right? But just for the purpose of my explanation, I'm going to tell you about capacity, throughput, and latency. Capacity is how much data you can store somewhere, right? You have some place that you can store data in, and you can ask yourself, okay, what's the quantity of data, right? In bytes or in terabytes. Throughput is how fast can you transmit the data. So this is in bytes per second or bits per second, right? How much data can you transmit per unit of time? We're going to call that throughput. And latency, the third one, is how much time do you need to wait until you start receiving data, right? If you ask for data, it might take a while until you start actually getting the data delivered to you, right? So this is called latency. Some people call latency something different. They call latency from the moment you request it to the moment you got all of it, right? So there are these 2 ways of defining it. But here, what I call latency for the purpose of this course is between the moment you ask for it and the moment you start receiving it, right? And then it takes a while to actually transmit the data. So let's take a look at these 3 and how they evolved in the past. So I'm going to rewind, again, go back in time, all the way to the 50s, 1956 to be precise. I looked for the first commercially available hard drive where you could actually store data. So the first commercially available hard drive that was by IBM, it was called the RAMAC 350. It was part of a computer that was sold. It had a capacity of 5 megabytes. It was incredible for the time. 5 megabytes. So that's what you fit. The throughput is a speed. You could read 12.5 kilobytes per second. Back then, they didn't say kilobyte. They said 12,500 characters per second, right? They called them characters. But today, we would say it's 12.5 kilobytes per second. So that's, again, capacity per unit of time. And the third one is latency, 600 milliseconds, still less than a second, right? But 600 milliseconds is the time that it took you. And that actually is gigantic because that's it's basically as high as I am, 1.50 meters like this, and maybe 70 centimeters of depth. But it's gigantic. All of that just for 5 gigabytes. Of course, today it looks ridiculous, but you have to, again, put yourself in the shoes of the people at the time. That was actually a lot. It's 5 million characters that you could store. What about today? If we fast forward to today, this, oh, I had a picture. That's the reason for the latency is because it rotates, right? And it needs time for the rotation to bring it in place so that it can be read by the reading head. All right, now this is what we have today. The largest that I could find was 22 terabyte. That's the Western Digital Gold WD blah, 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 blah. And in fact, it's so small that I have to zoom in a little bit. And you see that's a capacity of 22 terabytes, 291 megabytes per second. And the latency is just 2.384 milliseconds, right? And the volume is like this. Probably you already saw a hard drive, all of you. This is pretty much like this, quite thin. So of course, it's very tempting to compare how all of that actually evolved through time. So I ran the computations. I have a question that I want. Let me make progress. If I have time, I'll come back to this question, maybe after the break. So let's look at the progress that we've made in terms of capacity. Here I'm renormalizing per unit of volume to be fair, because it also shrank. It's not enough to just compare 5 megabytes to 22 terabytes. So I divided by unit of volume. This is the throughput, and this is the latency. And I'm not going to click anywhere because that's all already there. It's not that I have animations and the throughput and latency are going to appear. They're already there. This is by how much it evolved. And every year I come up with a different number because I'm not good with numbers and so on. But this time, when I recalculated everything, I found 17 billion of difference in terms of factor of capacity per unit of volume, 23,000 times more throughput. That's less than 17 billion. And 250 is the factor of latency. Careful, the throughput increased, the capacity increased, latency decreases. You want less latency, right? It needs to be as quick as possible. All right. Well, I don't know to what extent you realize that this actually means we are in big trouble. We are in big trouble because what this means is that the data we're able to produce and to store has massively expanded, but the speed at which we can process it is ridiculously small in terms of improvements compared to that. And that means big trouble. That's a logarithmic scale, just to show that they are here. So let me give you an example then, just for you to realize. And again, it's the orders of magnitudes with the numbers. I can share the spreadsheet if you want. Maybe you can try to find the mistakes and help me get the exact values, but the orders of magnitudes are there. So let's imagine that today there is a book that has a capacity of 600,000 words. That's the equivalent of our hard drive. Now the throughput would be, let's say, we read, or the average human can read 1,000 words per minute, right, from that book. And then the latency would be you're in the library and you need to get up and get the book, right? Maybe 1 minute, just for the analogy to be complete. All right. Now, if you look at what amount of time it takes to read the book entirely, you just do the division and it's 10 hours. Sounds reasonable, right? If you buy, I don't know, a novel by Dan Brown, it's pretty reasonable. You will be done by 10 hours if you really enjoy what you're reading, right? So 10 hours is today. Let's jump 2 centuries in the future. The United Federation of Planets, the Vulcans, and so on, so massive improvements. And then, and this is what I never managed to get right because it fluctuates a bit, but again, it's about the order of magnitudes. I put the same factors in there, 70 billions of factor that the book is bigger by. It was a weird sentence, so let's make the book 70 billion times bigger. And the number of words per minute, the same factor of 23,000, right? I took them from the previous slides. Now, to finish the book in 2 centuries, a typical book is going to take you 846 years. Who understands that we are in trouble, right? You cannot even finish the book in a reasonable amount of time any more, right? So this is really, really problematic. So this is really a huge problem. And in fact, this is the problem that big data technologies are solving. And this really is so important. You need to remember this through the entire semester. Almost everything we're going to see is actually a consequence of this. Because how do we deal with the discrepancy between the capacity and the throughput? We just parallelize, right? We parallelize. That's exactly what we are going to do with MapReduce, with Spark. And what that means is you just go to some social media and you ask 200 million people to each read a chapter of the book or something, and then you're done in 10 hours, right? So this is basically how it works. I can't guarantee the number. I can share my spreadsheet and you help me actually get the correct numbers, but again, the orders of magnitudes are there. So what does it mean for computers? It means in a data center, we're going to have a lot of machines like that, and we are going to spread the computations across a very large number of machines. And I'll talk about data centers next week. But of course, the same problem occurs with throughput and latency, is that we increase the speed at which we read the data, but the time it takes to start reading the data has improved by much less. So it means that if we keep the same technologies and just let this evolve according to these numbers, then we're just going to spend our entire time waiting. It's like you wait for a long time, and then the data is transmitted very rapidly, right? Then you wait again for some time, and then it's transmitted very rapidly. So what do you spend your time in? You're just waiting, right? And this is something that also some people have this problem when they have a database system. They just are stuck waiting for stuff. Then it means you need to solve a latency issue, right? And we'll see that can be solved with batch processing. And in fact, in MapReduce, in Spark, this is exactly how this is done, right? So parallelization and batch processing are the two ways that we are going to fix this during the semester. So what is big data? It's basically technologies that were designed to solve that problem, to basically solve the issue that the data we have grew with a discrepancy between capacity, throughput, and latency. That's pretty much it. Everything else, that's basically a consequence of this, a very natural consequence. So that will follow us during the next 13 weeks. All right? Now, big data is also everywhere in the sciences. That's data science, basically. Everybody is doing data science today. It starts with CERN, who didn't wait for the hype to actually start gathering data. So you have this collider in Geneva that just gathers a lot of data. In fact, it produces so much data that you cannot even store it all. So they have to design technologies that while the protons are actually colliding, it filters out the data you don't want to keep. And that is increasingly using machine learning and artificial intelligence to actually tell. So already when you record the collisions, you're already filtering a lot of the noise and just keeping a tiny fraction of it. Then you get a huge data set, because even after filtering, you're still in the petabyte range. And then you just filter and extract a subset of interest that you want to look at. And this is the one that is distributed to the community, to all the physicists for analysis. And then there is an even smaller subset that is for schools, high schools. So here they really take the part where the Higgs boson is, and then it's basically much easier to find. All right, but this is just huge. They have a lot of servers. I talked to you about parallelization. We're talking about 10,000 more machines, 400,000 plus computer cores. So this is just to show you the evolution of that, and that even stops in 2017. So you can imagine how it actually continues. Something else that scales a lot is mapping the universe, because there's a lot of people who are busy trying to build an atlas of the universe with all the stars, the planets, the exoplanets, the black holes, the neutron stars, the galaxies, everything we can find. And there are several phases. The last phase completed in 2020, I think, and that's also gigantic quantities of data. It's public. You can download it and analyze it, in fact. But it's gigantic, and that doesn't fit on a single machine, as we will see. This is also an example related to CERN. That's a paper that we wrote right here at ETH with physicists, just to evaluate the use of query languages in how you analyze all of this data coming from CERN. Because we realized something. The physicists were not actually using SQL. You would think, you know, the natural thing to do if you analyze data is to use a query language like SQL, but there weren't. So we tried to investigate a little bit why that was the case. And in fact, a lot of that has to do with what we will cover in this semester about the difficulties and limitations of SQL, right? Okay. But the paper is out there for whoever wants to read it. It's going to ring very soon. So I am talking knowing that I will be interrupted by the ring, but I'll just stop whenever it rings. We are also trying to sequence the entire genome. In fact, very recently, we even got the Y chromosome sequenced. So now we are complete. And that's 3 billion base pairs. That also needs to be stored. And in fact, we are even started to make so much progress that we can even edit the DNA. Again, the ethical considerations should also play a role here, but at least technologically, there's a lot that we managed to do today. Speaking of DNA, there are people, I'm thinking of a colleague of mine who was at ETH, Thomas Heinis. With his team, they managed to actually use DNA to store relational data and query it, right? And with this excitement, I'm leaving you for the break. So we'll be back in 15 minutes at 3:15. Then we'll continue. I'll introduce you to the TA team, and then we'll start brushing up with SQL. So see you in 15 minutes. Thank you.